Hello everyone, thank you for taking the time to attend this presentation. My name is Paul Ng, and I'm a test engineer from Facebook's network hardware engineering team. Today I'm joined by my colleague, Ahmad Gawi, and our partner Surendra Anabolu from Broadcom. And we're here to talk to you about F16 in a box and why we needed to build this for use in the lab. Now, before I can explain what F16 in a box is, we should start with one of the fundamentals of hardware engineering, testing hardware. When we build a piece of hardware, one of the questions we always ask is, how does this piece of hardware behave in a data center environment? And most people do not have the luxury of having their own data center to test their equipment in. We challenged ourselves and asked, how do I replicate this environment to the lab setting for the use of testing? And that conclusion led us to the solution of F16 in a box. The idea behind F16 in a box is to simulate a data center environment inside the lab, creating the relative numbers of hops a piece of equipment would need to take in order to talk to another piece of hardware in the data center. Just last year, in the OCP summit, Facebook introduced our F16 architecture. Just to quickly recap on what this is, it is an architecture where we connect the top of rack switches to fabric switches, which in turn connect to spine switches. This architecture provides us with reduced complexity from our previous designs, with a 3x reduction in the number of chips and a 2.25 times less tiering of chips in the topology, greatly simplifying our network design. So the question arises, why build F16 in a box? Some of our primary motivators is to port the environment to a different users for simulation without the need to incur the cost of actually building a data center style setup in your lab. It provides a safe, controlled environment to use as a one-stop shop which gives you the ability to control different parameters like buffer pressure and making it completely observable at all points in the network. This provides a comprehensive environment for you to view different hardwares and how they behave in the lab environment. With that, I will hand it over to Surendra for the next part of this presentation.
Hi, this is Surendra Anabolu here from Broadcom. So Paul has given you the motivation on why we need F16 in a box and the design principles behind the F16 network and also F16 in a box. So as Paul has explained, like we want to simplify the rollout, the testing, development of tools on top of the F16 fabric. And to do that, we want to simplify as much as possible, minimize the requirements from the user on the number of components that they need to bring this together. In F16, there's Tomahawk 3 devices that are used, and we used a Tomahawk 3 switch, and that actually emulates multiple components that you need to validate or test your applications on it. So if you think about it, like F16, as Paul has shown, there are multiple switches out there in the F16 network. And what we are looking at here is, we looked at, can we virtualize these switches so that maybe with one single switch, you could simulate the entire F16 network. So you need multiple virtual switches to do that. And then in F16, the Ecmp is extensively used. So we definitely need, as a requirement, we definitely need multi-way Ecmp paths at every stage that's available. This is what I get from Paul. And then the next step is, okay, now you have the boxes, multiple switches, and then you have Ecmp paths. You need to stimulate this fabric. You need to run the test traffic over this. So you do need a traffic generator. Traffic generators could be quite bulky, or like especially to test at the scale of F16 would be significant. So we took that as a requirement for our users to have a built-in traffic generator in this F16 in a box setup. And then the next step is, okay, you have a traffic generator, but then you need to analyze and see, okay, what is the performance of my application that's running on this? Like, how is the congestion? How is the fabric responding to my application? So the timestamping is a key part of this one. So early on, we set the requirement that timestamping needs to be supported in this setup as an F16. Ahmed will get into more detail on the packet timestamping a little later. And then the next component that to talk about is in any realistic network, there's going to be congestion, and you need control from the user to say, okay, I want to simulate how my application will behave if there were to be congestion. What if there's a congestion at rack level switch or a fabric switch? How does it behave? How does that affect the timing or like latency or like are there going to be packet drops, and how is that going to affect, how is my application going to respond to that? So there are many components that we're putting together into the one that we're showing you on the right-hand side, which is a Tomahawk 3 SPK. And F16 in a box is all these things in one. So it's all of F16 in a box, along with this traffic generation, timestamping, congestion generation, and everything together. And another requirement I get from Paul and Ahmed is that all of them need to be user configurable. Right? So we have all this set of components. They need to be user configurable. And then Tomahawk 3 inside, of course, it's a 12.80 switch, and with the ports speeds, it supports the 400 gig port speed. So you'll get multiple 400 gig ports that you could connect in the way that you need for simulating the F16 fabric. Next slide, please. Okay. So now let's go into step by step. So first we said we need virtual switches, and then we need Ecmp. That is that's used in the F16 fabric. So the way it works is, in F16 fabric, you get a set of scripts, and in these scripts, you will be able to set up which ports belong to which virtual switch. So you could have multiple switches, like in this particular example, I'm showing you 7 switches with 3-level hierarchy that can have like 5 hops to go from source to destination. And you could configure that in a script that shows, okay, here's the port number 24, 25, and 26 that belong to one switch. Let's have a group 1 and go and so on. You could configure that. And when you run this one Tomahawk 3 switch SPK would look like 7 switches for all the traffic. So that's number 1 is this virtual multiple switches that are simulated within one. The next one is Ecmp. Ecmp is an important part of it. And also in a real network with large number of links, you have a lot of cables to connect to. When you are simulating them with internal switch links, the internal switch links actually do not need a cable. And that was an important requirement that working with Ariel that we hear that is that, okay, let's make it such that it's easier for the users. So the Ecmp, the internal links do not require any cables, and they're wired internally. Once you have Ecmp figured out, the next step is like, how do you generate a traffic? And the traffic source, once you have the setup up and running, you have 2 choices. Either you can use a server, like a real server, to generate the traffic and see how it works. You could use an internal server, internal traffic generator. The internal traffic generator could target any of the queues. And you can have a combination of the both. That is, you have servers that are talking to each other. Then you can have an internal traffic generator that can target any of the queues at any level of the hierarchy to cause the congestion. So, and then see how your application responds to it when there's a congestion at that particular level. Next slide, please. Okay. So here we get into a little bit of detail on how the traffic generation works. So we have the switch box has a CPU, and then Tomahawk 3 can work as an amplifier in a way. It can generate the traffic by using multi-stage amplification. So the limitation is CPU itself can only generate maybe, let's say, megabits per second, maybe a gigabit per second. It's not more than that. But then usually, if you want to congest a high performance network like F16, you need 100 gigabit, maybe a terabit of bandwidth, or maybe even more than that. How do you do that? So this occurs in this setup by using replication, where you could have multi-stage replication, and where you could multiply by 100 times and then by another factor of 200, eventually giving you a factor of 100,000x. So something as simple as a 10 megabits per second could turn into a terabit per second. So there's multiple things are supported. There's single stage replication supported, multi-stage replication supported when you need terabits per second of bandwidth. And this is also achieved by using the internal switch structures like the shapers that are available. And this allows us to have control over how many, like what are the flows that you want to generate, and then how much traffic you want to generate, and what is the duty cycle, and what is the packet size. By that, what I mean is, in a test network, you may want to say that, oh, I want to generate a burst traffic, and that has, let's say, 30% duty or 20% duty cycle. The on time is so many, like a second or so many milliseconds, and the off time is so much, and the rate is this much. Like you can specify that. And then you could also specify what is the flow tuple that you want to use. You could actually completely construct what kind of a flow and what are the complete phi tuple for that particular flow. And what is the packet size or packet size ranges you want to use for generating each of these flows. And then you can also specify what is the target port that you want to congest with this traffic on. So by using all these knobs that you have available, which is like how much is the target rate and what is the duty cycle, what's the packet size, you have full control on what port to congest and what rate. And in addition to that, you have the ability to use specify the flow tuple. The flow tuple here is important because you want to be able to, this traffic also to follow certain path along your Ecmp. Okay, so, and that's good. So let's go to the next slide. Okay, so then the next level of control that we wanted to provide to the user of this setup infrastructure is, okay, so sometimes you have traffic flows in a real network that goes through only one hop, or maybe it could be 2 hops or 3 hops or 5 hops. It could be multiple hops, depending on what is the source and what is the destination, where who is talking to whom. So maybe you have traffic that goes to only intra-rack traffic within the pod or outside the pod. Depending on that, in a real F16 fabric, it takes different number of hops. So we want it to be faithful, and we want to be able to give you the control on this aspect of the traffic flow. So by using the scripts, you do have control over each of this traffic and how many hops it is taking. And you typically do that by specifying which server is talking to which server, and by putting them together in the appropriate rack switch, or maybe in pod level, or in the fabric level, or the spine level. So in this particular example, if S1 were to be talking to S3, the Ecmp paths will be taken such that you will see 3 hops. It will go to RSW1, FSW1, and RSW2. But if it were to be talking to S4 in another way, you could make it go through 5 hops, going all the way up to spine layer. And this is achieved by us providing a virtual switch that has its own routing table. So each hop is making its own decision on how to route the traffic through. So that way it is actually emulating how this will actually work in a real network. The other level of fidelity that we want to get to is the Ecmp. So the Ecmp, as I said earlier, is an important part of the fabric. So here we have using the Ecmp that is as if it's a regular switch. So all the regular RTAG hashing, the hash mechanisms, everything will work in this as if it's in the fabric. TCP/ISM paths allows each virtual switch to have connectivity at any level. So and that way that you're not actually, you don't need to cable, but you're still getting all the benefits of sending the traffic through multiple hops. Next slide, please. So, okay, so now we'll get into a demo of how would it look like these 2 switches, they're talking to each other, RSW2 to RSW4. And so first we'll go through briefly, and they're talking to each other, how the latency looks like, and then we'll cause a congestion and see what happens. Remember that I think usually each hop is much less than a microsecond latency. So when you go through 5 hops, you'll see a few microseconds of latency. Next slide, please. Okay. So here, what we are doing is this one we are going through live on the lab setup. We are using the iPath to simulate the traffic. So here we just started traffic on 2 hops, and 2 servers sending to the 3rd server, and 2 servers talking to each other. Here you see that the latency is about 3.2, 3.4 microseconds as it's going through. And you see that because it's going through 4 hops, and then but then you see that the latency is pretty steady because we haven't introduced any congestion yet. So, but once we introduce the congestion, then you'll see that the latency could change as well. So this is basically showing you the latency chart. Here, what is happening is the traffic is actually being directed to a server, whereas the browser is actually looking at the timestamps to figure this out. Next slide, please. So here, then we go through, then we are going to start traffic at a third node, and then this is going to cause congestion at one of the links. And as it is playing through, you would, okay. Can you go to the next slide? Okay. So that's what was happening was that in the demo video configuration, the one on the screenshot on the right-hand side is showing that when the traffic was started, then the latency goes up, and then you'll see that, okay, the latency is varying there because of the congestion and the burstiness in the traffic. The other thing I want to note here is that the timing was an important component of how we are able to get this latency information. It's because with the timing, the destination is able to see what is the timestamp at the source, and destination is able to figure out the latency. Next slide. So the timing is an important feature. So what happens is the switch at each hop is able to put a timestamp that tells you what time it came in and what time it left. Right? So Tomahawk 3 supports the trailer timestamp that has the components that says the UTC timestamp, and also is it the receive timestamp or the transmit timestamp. And the packet size grows in the length. Next slide. So when you put this timestamp together, and this timestamp happens at multiple hops, you can actually put the path together. Tomahawk 3 supports stacking the node metadata. That means every node is adding the timestamp. So you could actually see how much time this packet spent at each one of the hops. And there's a clear indication of the hop numbers contributing to the latency. So you could say, oh, it's the hop number 3 that contributes latency, and here's the ID of the hop number 3. So that switch is actually congested. You could say that. And this is added to the real time to the active packet. And this helps with you to trace the packet path as well. So you know actually it went through 3 hops or 4 hops, or did it go through which switch it went through. Next slide. So here I hand it off to Ahmed.
Thank you, Surendra and Paul. So as one of the like high-level applications for the F16 in a box, we wanted to basically benchmark and evaluate the servos and like the mechanism, like in general, the PTP implementation, how it will look in the future F16 architecture. So one way is obviously like let's say the SSW, FSW, RSW, which comes with its own advantages and disadvantages. And the other one is like basically using this F16 in a box platform. So a little bit of the architecture that we are thinking about that we want to use basically for the PTP. We want to use basically a grandmaster that is connected to the SSW, as you can see in the diagram. And SSW and FSW, they will act basically as the transparent clocks. And the RSWs, they will act as the boundary clock. So this will be basically the first layer for the PTP, which we are estimating something about 5,000 RSWs, which the time basically will disseminate from the ground. You have basically, from the boundary clocks that they are basically the RSWs, you have an estimate of, let's say, under 100 servers that they will interact with the boundary clock. It's going all the way to the grandmaster. So that basically helps with the scale that we're going through. So some of the early potential users for this like accurate time PTP, they demanded error bounds, and error bounds are a little bit hard to measure if you don't know how many hops you go through, because like the way, like the the most like useful way, let's say the used way today for measuring the error bounds is you look basically at the changes of like the servo, the values of the servo, the correction, like the correction that the servo puts in. The correction that the servo puts in is with respect to the hop, like let's say in case of the servers, it's with respect to the boundary clock. You may have the previous data. You look at the previous data and you see like there is a correction, let's say within 100 nanoseconds, while the boundary clock itself is basically within let's say 500 nanoseconds from a grandmaster. So from the second layer, which I have it here written PTP2, you will not have an easy time to measure how much like basically jitter you are having with respect to the grandmaster. So to do this, basically it is important to have, let's say, those hops in the metadata for those hops already placed somewhere in the boundary clock. So beneath the boundary clock, they go through their jitter. They would consider also the jitter that the boundary clock has with respect to the grandmaster and provide that to the application to know the total error bound that the data that is presented to has, because that will then determine the range that the application can consider in terms of causality, and you will never have an issue of, let's say, pulling time that belongs to the future. Yeah, I will hand it back to Surendra.
We want to give special thanks to the people who made significant contributions here. Ariel guided all of us in the process, in the project, and the ideas, and very special support in the higher level guidance, guiding this project in the development. Ramasamy Lakshmanan is the CSG Performance Lab lead from Broadcom, who went through the scripts development and lab setup and working on this one. And along with Sudarshan Suresh, who's at the researcher at the CSG Performance Lab, working with us in developing the scripts. Thank you.